Hello everyone. Today I am here to present a topic named it as photonic crystal fiber, which is one of the research area in my PhD work, in my research work. My name is Satyaprakash Raut. Currently I am a research scholar in the School of Electronics Engineering, Kalinga Institute of Industrial Technology, Institute of Eminence, Bhubaneswar. So coming to the outline of my today's presentation, today I'm going to narrate what is the introduction to PCF, then what is the difference between a photonic crystal fiber and conventional optical fiber, and then types and design of photonic crystal fibers, like what sort of designs and what sort of core cladding arrangement has been done along with the air holes. Then I will going to discuss about the surface plasmon resonance, which is one of the key physical phenomena make the photonic crystal fiber to be acting as a excellent sensor, or basically behaves as a biosensor. Then to realize this PCF virtually, there is a simulation software named it as COMSOL Multiphysics, which basically gives the detail knowledge related to a model, not only on the mathematical point of view, but also mainly focusing on the multiphysics concept component of it. Now coming to the introduction of PCF, so photonic crystal fibers are basically a special type of optical fibers that are completely based on the property of photonic crystals. As we know that there are different type of photonic crystals are there: one-dimensional photonic crystals, two-dimensional photonic crystals, and three-dimensional photonic crystals, right? Now this the basic difference between a photonic crystal fiber and a general optical fiber, whether it may be a single mode fiber or maybe a multi-mode fiber, is that a photonic crystal fiber is basically contains an array of air holes basically surrounded the core and basically present in the cladding region. So as these holes are completely microstructured in nature, and these holes are basically arranged either in hexagonal format, or either it will be represented in any kind of polygonal shape or any kind of decagon shape and all. So it is basically known as your microstructure fiber, and it is also known as holy fiber, as it basically contains an array of air holes basically present in the entire length of the fiber. Okay, now in this particular picture which I took it from the ResearchGate is basically depicting two types of photonic crystal fiber. The first one is basically contains a solid core which is completely surrounded by air holes. So this solid core photonic crystal fiber is also known as index guiding photonic crystal fiber. And in the second diagram of photonic crystal fiber, that is in B, it is basically contains a hollow core. That means this air hole is basically surrounded by a core which is completely hollow in nature, that is air is basically filled over there, whose refractive index is 1, and in the solid core the refractive index is 1.4, which is nothing but a silica. Now this photonic crystal fiber is actually a three-dimensional fibers bracts grating consisting tiny air holes in the fiberglass, completely surrounded across the core, which basically confines the light in the core region of the photonic crystal fiber. Now coming to the different types of photonic crystal fiber. Photonic crystal fiber is broadly categorized into two types. One is index guiding photonic crystal fiber, and another is photonic band gap, that is PBG photonic crystal fiber. First one is IGP for IG photonic crystal fiber, or it is also known as SCPCF, that is solid core photonic crystal fiber. And the second one is photonic band gap photonic crystal fiber, that is PBG and HCPCF photonic crystal fiber. Now coming to the difference between these two type of photonic crystal fiber, as I shown you in this particular in the earlier figure, I shown you the two types of photonic crystal fiber. The A depicts a solid core and B depicts a hollow core, right? So in the index guiding photonic crystal fiber, this type of photonic crystal fiber is basically comprises of a solid core along with an array of air holes running across the entire length of the fiber. Now coming to the photonic band gap photonic crystal fiber, this is basically consists of a hollow core in which the core material is completely dipped with air, whose refractive index is equals to 1, and it basically comprises of air holes taken in the form of an array, and it is basically present in the entire length of the fiber. Now coming to the index guiding photonic crystal fiber, as the core is completely solid in nature, and and it is surrounded by air holes whose refractive index is 1, and the entire cladding region is taken as silica. So if you take the resultant refractive index between the air holes and the silica, the resultant refractive index is quite smaller than the refractive index of the core region. So due to this type of photonic crystal fiber is basically possesses a positive refractive index profile. So due to this positive refractive index profile, where the core of the refractive index is greater than the cladding refractive index, so it basically follows the principle of total internal reflection of light, which basically says that when a light moves from the denser medium to a rarer medium, that is from a high refractive index zone to a low refractive index zone, then with the angle of incidence greater than the critical angle, then all the light will not pass through the rarer region, right, but rather it will get reflected back into the high refractive index zone or the denser medium. So the same way, when the light basically propagates inside an optical fiber, the light will not get refracted towards the cladding region, but it will start guided inside the core region. Now this type of photonic crystal fiber is also called as convectional photonic optical fibers, as it basically follows the principle of total internal reflection of light. Now coming to the photonic band gap type of fiber, as air is there as a core, as air is basically present in the core, as the core is hollow in nature, so refractive index is definitely comparatively lower than the refractive index of the cladding region. So this basically follows a negative refractive index profile. So this type of photonic crystal fiber doesn't follow any TIR principle, but due to the photonic band gap effect, as the core region is completely hollow in nature, so there is a defect arise in the core region. So due to this defect, there is a change in the optical property arises. So the light will be completely guided by the concept of photonic crystal principle. Now these are the shots of designs for different PCFs approved by different scholars from different parts of the country. Now the first proposed design of PCF and its corresponding application and the corresponding author I have taken. Now first type of proposed design was done by rectangular slotted porous photonic crystal fiber, which is whose application is nothing but detection of carbon dioxide gas. And the second type of photonic crystal fiber, which fascinates a lot, because it basically contains geonex. It basically contains a geonex based D-shaped photonic crystal fiber. Geonex is one right now the current material which basically gains a lot of attention towards the scholars and scientists who are working on photonic crystal fibers, as geonex is basically providing high sensing effect while using the photonic crystal fiber. Now GNX is basically provides low birefringence, low confinement loss will be there while using GNX as a material to be dipped in the cladding region. Simultaneously, GNX is also providing low dispersion effect also. Now when the researcher basically taken GNX and the shape of the core has been taken in the D shape, that means the entire shape of the photonic crystal fiber or its geometry has been taken in the D shape format, and its primary application is nothing but is chemical sensing. Then hexagonal shaped hollow core photonic crystal fiber has been taken, which basically used for finding out the different harmful additives which is widely used in daily foods provided to the people, like saccharins and sorbitols. Then tricore PCFs. So in this particular type of photonic crystal fiber, there are three number of cores is basically there. Now in this three number of cores, the analyte is to be poured in there. Now then tricore PCF, which is widely used for salinity and temperature detection. Dual core SPR. SPR stands for surface plasmon resonance, which I will talk about it in the next slide. Now dual core PCF is there. The photonic crystal fiber basically uses the principle of surface plasmon resonance, along with the geometry basically contains a dual core surrounded by air holes in the cladding region. Now monorectangular core PCF, in this type of particular paper, the author has basically taken the core in the rectangular format, and this type of design is basically used for blood cancer detections. Then blended PCF based surface plasmon resonance. So in this type of photonic crystal fiber, surface plasmon resonance principle has been taken, but the bending is basically happened in terms of the geometry. Okay, so that means part of the geometry got sliced out in the form of a curve. So due to the slicing of that particular geometry, it basically called it as a bended photonic crystal fiber based on SPR principle. Now graphene is also one of the material that basically gets coated over the photonic crystal fiber to make it as an excellent biosensor. Geonex, when I'm talking about Geonex also, right now Geonex, as I told previously, that Geonex is an excellent material right now. It's basically catching the eye of every scholar who is working on the area of photonic crystal fiber, is that basically it provides low bioreference, and it provides an excellent sensitivity when the photonic crystal fiber basically used as a sensor. Then dispersion effect is very low. Non-linearity effect is also will also be like considered when you are basically taking the concept of Geonex as a material. Now some of the photonic crystals fiber that has been used, which basically depicts the feather of a butterfly, or that is called as bio-inspired butterfly core-shaped photonic crystal fiber, which is basically used for real-time biomolecule detections, or biomolecules in the sense that it may be either used to find out the cell detections or any kind of protein detection in DNA and everything. It will be useful. Now the graphene coated SPR PCF is basically used for detection of SARS-CoV-2 virus. Now two of the researchers are basically there from China who started working on this type of photonic crystal fiber by the concept of surface plasmon resonance, and they basically done the coating of graphene, and they basically try to use it to detect the SARS-CoV-2 virus easily. Okay, so SARS-CoV-2 virus basically what they basically did is that they basically found the wavelength at which the wavelength at which the light will get reflected back. Then what about the sensitivity? They have studied the relative the relative sensitivity, as well as like what are the changes, the reflective intensity curve also they found out with respect to the wavelength also, so while detecting the SARS-CoV-2 virus. Now coming to the important topic, which basically makes PCF as an excellent sensor and basically used it as a biosensor, is nothing but surface plasmon resonance. So what surface plasmon resonance is talk about? So surface plasmon resonance is actually one kind of phenomena that occurs when a plane polarized lights hit a metal film at the interface of the media with different refractive index. Why it is? When the different refractive index will be there, the refractive index will occur when we are basically using an analyte, and when the solution will get added into that particular solution is basically added in the form of analyte, there is a change in the refractive index basically occurs. Now you can particularly see in the particular figure is that it basically contains a prism, a light beam, and a reflected light. So reflected light will be obtained once the light beam passes through the prism. So a polychromatic light coming from the light beam is getting converted to a monochromatic light, and it will basically going to strike the interface, that basically nothing but the interface between dielectric media and metal film. Either it will be coated with silver or coated with gold. Is basically gold coated film is basically taken. Now the reflection that basically comes out after the surface plasmon resonance, now what happens that it will be going to be detected in the detector. Now what happens over here? Now this SPR technique is basically excite and detect collective oscillation of free electrons, which is basically known as your surface plasmons, which basically propagates on the interface between the dielectric and metal film. okay, by the Krichmann configuration. So there are two type of configurations that is basically there. One is called as auto configuration, another is called as Krichmann configuration. And in Krichmann configuration is basically used for SPR technique, in which light is completely focused on a metal film through a glass prism. So we basically take a glass prism. Now what is the necessity of taking a glass prism? Now glass prism is basically when a polychromatic light that contains multi-wavelength component in it or multi-frequency component in it, it basically converts that multi-component wavelength or multi-frequency component light into a monochromatic light that basically contains a single wavelength. Understood? Now, and the subsequent reflection is detected with the help of the detector. Now at a certain angle of incidence from the light beam, or that I called as a resonant angle. That means the incident angle will be called it as a resonant angle, and this resonant angle is nothing but that angle at which the plasmons are said to resonate with the light wave. Right, now the resulting is nothing but the absorption of that light at that particular angle. So at that particular angle, some portion of the light or the intensity of the light will get absorbed. So it basically creates a dark line over there. It basically creates a dark line in the reflected beam, which is basically going to be detected at the detector end. Right, now those dark line basically contains a wealth of informations. What it basically gives us the informations, it gives us the information is that there is a change basically happen. There is some kind of like information it is giving, that it is basically giving the information of detection of salinity or temperature, detection of blood cancer cells, detection of breast cancer cells, detection of SARS-CoV-2 virus, then detection of alcohol, in the detection of the amount of adulteration happened in the alcohol, detection of carbon dioxide. So all these type of sensing mechanism can be obtained by the principle of surface plasmon resonance. Now the dark line basically contains a wealth of information, that this information is nothing but the changes that basically happens, like some irregularities there in their molecule, which basically gives us a dark line. Okay, and this dark line is basically obtained due to the resonant angle at which the absorption of light will take place. Okay, now the resonance angle can be obtained by observing a dip in the SBR curve. So you can particularly see, you can particularly see this particular curve, right? This particular curve you can see, which is the plot drawn between the SPR reflections intensity versus the dip angle. Okay, so this curve basically shows that there is a dip in the angle occurs. That means at that particular wavelength the light got absorbed and it is completely dark. Okay, and it will not get absorbed. Right, now a shift in the reflectivity curve. So this is basically called it as a reflectivity curve. So if I'll go to the particular figure which is drawn between the SPR reflection intensity versus the dip angle. So there is a dip occurs between 70 to 75 nanometer range. Okay, now in that particular that is I can say that it is 72.5 nanometer, that is a dip occurs. Right, so this shift in the reflectivity curve represents that the molecule is getting binded. The molecule is getting binded, event taking place or near to the metal film, right? So that means these biomolecules are coming and basically getting attached to this particular ligand. So these biomolecules which is coming, which is there in the form of analyte, when it is coming and basically entering into this particular interface, now these molecules will going to be attached with this particular ligands. So due to the attachment of these ligands, there is a shift in the curve occurs. Okay, there is a shift in the curves occurs, or there is a conformational change in the molecule bound to the film occurs. So there is a shift in the curve occurs. So due to the biomolecules getting attached to this ligand, and when there is these solutions are more and more solutions will going to be added, there is a change in the refractive index occurs. So due to the change in refractive index, this SPR reflection intensity curve will also going to be changed. Now initially when it was there between 72.5 nanometer, now it got to change to 82.5 nanometer. So this is the total explanation related to the surface plasmon resonance. So surface plasmon resonance, as I can say, that it basically contains a light beam. It also contains a prism based it is also contains prism based arrangement is to be there. Then this prism based arrangement will be present between the interface of the dielectric medium, which is a low permittivity medium, along with a metal film medium whose permittivity is positive in nature. Now there are some ligands are present, and the analyte is basically added, the solution in the form of analyte is basically added, and when these biomolecules will get binded with these ligands, there is a change in the SPR reflection intensity curve will be happen with respect to the deep angle. Now coming to the simulation point of view of photonic crystal fiber, either we are simulating a normal photonic crystal fiber, or either we are simulating a SPR based photonic crystal fiber, or either a solid core photonic crystal fiber, or either a hollow core photonic crystal fiber. The primary thing is to design the software virtually, because sometimes happen is that it is not very. So sometimes it happens that physical experiment at everywhere is not possible due to cost factor of some. So this PCF will going to be designed, and its corresponding geometrical shape will be designed by the help of COMSOL multiphysics. So it basically gives you a virtual environment where you can easily create the physics model that give you a live experience of the particular phenomena you want to observe. Then it is actually a software based on advanced numerical methods, fully coupled with multiphysics modeling technique. Okay, and this COMSOL is basically helpful for designing a PCF in a very simpler way. So first what you have to do, you have to open the COMSOL multiphysics. In that COMSOL multiphysics, once you will open, you have to take the 2D geometry of it. So once you're taking the two-dimensional geometry, you have to go for the study. What kind of study you need to do? So you have to study the electromagnetic waves, you have to study. Then once the study has been done, then finally we'll go to press the done button, and finally the COMSOL application will open, and the interface will also open, where you will see a number of number of boxes will be there, like touch boxes will be there. In the COMSOL modeling workflow, there is a certain number of steps that needs to be followed. First one is nothing but setting up the model environment, and second one is building the geometry of the objects. In geometry of objects, you will need to find different geometries like circle, rectangle, ellipse, polygons, decagons, and everything you will find it out. Then once the geometry will be fixed, then we need to go to the global definitions, where you need to define what sort of parameters that needs to be taken, which will be used in the entire work process. In case of PCF, we need to define the radius, diameter of the air holes. We need to define the pitch between the air holes. Then we need to define the operating wavelength, and all sort of parameters, optical parameters, needs to be defined in the global declarations. And in the component sections, we need to build the objects, geometrical objects. Either it may be a circle. In PCF, we basically follows a circular shape, so we need to go for a circle to be selected, and in that particular circle you need to select the particular radius, and while selecting the radius, it will ask you in which angle you need to keep that circle and what is the respective position of that circle. It will be asked. Now then after the geometry will be done, after the geometrical shape of the PCF will be done, then finally we will go to the addition of materials. Now for COMSOL multiphysics, the lots of materials are available, like graphene, zinc oxide, titanium oxide, then silicon, germanium arsenides, air, geonex, and so many materials are basically available. So depending on the requirement on the PCF, and make it as an excellent sensor, what sort of the sort of materials that basically used, we need to be select from the component sections. Here there in that component section, there is a subsection is basically there known as your material. In that particular material, we need to search what material is going to be added in the air holes, or what materials will be added in the cladding region. Okay, then after the material selection will be done, then you need to define the physical boundary conditions. So different boundary condition needs to be defined. Then after defining the physics boundary conditions, we need to create the mesh. Now once the mesh will be created, you need to see the mesh either in extra fine condition, finer condition, normal condition. Then once the mesh will be created, then you have to go for run study operation. Then you have to go for run study operation. In that, you need to select the operating frequency. You need to select the number of modes that needs to be traveled inside the core. Then once the output will be obtained, once you will press the compute button, the simulation will work for half an hour to 1 hour or more than that, depending on the processing speed of your system. Then once you are basically getting, there is some post-process results will be obtained, like just now I shown you like the relationship drawn between the SPR responsivity curve versus the deep angle, and also the SPR responsivity curve with respect to the wavelength. That also we can find out the plotting done between the confinement loss and the wavelength. Then what is the effect of what are the different nonlinearity effects and its corresponding graphs can also be obtained. Dispersion effects on PCF also can be studied over there. Okay, now once you are basically creating a live model and whatever data you have basically given, and what sort of parameters that you have taken, or the different parameters that you have taken, if it is giving you a very good result, and if you are finding something new, you can build a simulation app that can be useful for the other researchers who are basically landing new to this PCF, who are basically landing to this PCF world, can use this particular simulation work and can get the result in a very quicker way. So thank you so much for giving me this opportunity for giving a presentation on this photonic crystal fiber. I hope that I have given a very good presentation, and I have cleared all the parts, and I have touched all the parts of photonic crystal fibers and its corresponding applications, and what sort of designs that has been taken, and what sort of designs are being currently be there in research work by different researchers across the world. Then what sort of what is the importance of surface plasmon resonance to make photonic crystal fiber to be behaves as a biosensor for detecting different biomolecules or protein cells or protein molecules. Then we have seen about to realize those by SPR based PCF biosensors, you need to go for a virtual environment where there is no where there is no possibility of creating a physical model of that particular research you want to do, but in that particular, but you have a virtual model environment or simulation software where you can lively simulate the PCF with SPR based technique, and you can use it as a sensor. Thank you so much.